Yeah. Uh, Please go ahead.
I'm going to talk about, yeah, so I mentioned that there are two, great results about Groebner bases for matrix Schubert varieties. And um, the, uh, I guess in the Knutson and Miller result, they really produce a Groebner basis. Like it, they list a bunch of polynomials and they're Groebner bases. In the Klein-Wygant result, they don't quite do that. They don't actually produce a Groebner basis, but they just describe the initial degeneration. But like, nevertheless, it's a natural question to ask. Um, okay, you had like two, choices of W that give you interesting things. Can you understand like what happens for all possible choices of W? So can you look for a universal Grobner basis? So, of course, this is like a very, uh, I don't know, probably you should expect it to be a very difficult question. But talk about what we can say. So first of all, I'm going to describe a bit what the ideal of XW is. And so to do that, I'm going to say, um, uh, how our well, for one thing, I'm gonna fix conventions and tell you what the ideal of XW looks like. So okay, so I have here a Roth diagram of a permutation, and then so at each of these points you have some here. So this is like the label, yeah, IW of I. And so this diagram corresponds to a permutation in the following way. So you look at the first row, and then you get 6 is the dot is at the 6th point. In the second row, the dot is at the 4th point. Third row, the dot is at the 5th point, and so on. So you produce a permutation in this way. 10, 7, 8, 9. Okay, so there's a permutation like this. And then, so maybe this is pi. And then here's how you write down the ideal of the matrix Schubert variety, the ideal of XW, in my conventions. Um, so for each, after you draw these sort of dark, like death rays shooting out down and to the right of each of the uh, points in the Roth diagram, the IWI. And then for each point that isn't crossed out, you write a number, which is the number of dots that are up and to the left. So for example, all these points, there are 0 dots up and to the left. Here, there's 1 dot up and to the left. And then for these 3 points, there's 1, 2, 3, 4, 5 dots that are up and to the left. And then what the matrix, the ideal of the matrix Schubert variety is, yeah. So what the matrix Schubert variety is it's the locus where each sort of submatrix in the sort of given in the various regions has rank upper bounded by the numbers in red. So for example, any submatrix in this region has rank at most 0, so i.e. the entries are all 0. Any matrix in this region has rank at most 1, and any matrix in this region has rank at most 5. So the ideal of XW is defined by sort of north minors of this matrix, so that the rank of maybe I'll just say the ranks are bounded by the numbers in red. So for example, you would include any 2 by 2 minor that is sort of living in these rows, so as to guarantee that this matrix, for example, has rank at most 1. And then you would include any 6x6 minor that lives, in this region. So Fulton showed that these matrices, and in fact, he gave like a slightly more efficient set of generators. Yeah, he showed that these guys generate the ideal of the matrix Schubert variety, and we're going to give a universal Groebner basis for some family of matrix Schubert varieties, and we have some list of polynomials, and they're based on sort of starting with these generators and then modifying them in some way and adding more things. So before I can tell you what our set of generators are, I need to tell you what's called the CDG generators. So this was these are somehow, I guess, implicit in a paper of Konka, De Negri, and Gorla. There's something simple. So what you do is you take like a minor, which is 0, which is in the ideal. And what might happen, so that minor, it corresponds to some submatrix. And what might happen is that so maybe something like this. What might happen is that some of the entries in that matrix are 0. So, you have these entries, which are sort of forced to be 0. And it might happen that you have some minor, that looks like this, where maybe 2 of the entries are 0. And so rather than adding the determinant of that matrix, the submatrix, to your ideal, what you do is you first 0 out these entries and then take the determinant. So 0 out entries in the rank 0 part. So if you take that for every like non-rank 0 minor, and then you also include like the rank 0 minor, so like A11 is a CDG generator, but also you take whatever this 6x6 thing, or maybe this 6x6 thing, and then you set these two entries equal to 0. That is a CDG generator. Okay, so it's some sort of not too complicated modification of the generators that Holton gave. Okay. So we then modify these generators a little bit more. Okay, so here it is. So we define a set that we call RW, which we will show that under some circumstances is okay. So sorry. We will show that it is in some settings a universal Groebner basis for the ideal of XW. And it's based on, you take the CDG generators and then you do some operation which we call merging. So okay, so here is what merging is. So again, it's something not very complicated. So suppose you have two polynomials, and f1 and f2 in maybe these n squared variables. So they live on their polynomials in CD n squared. And so I can suppose they could be written as A alpha beta times G1 plus R1. And I have second polynomial, and I can write it as A alpha beta G2 plus R2. And I'm going to suppose that G1, G2, R1, R2 are not divisible by A alpha beta. Okay, so basically the F1 and F2 are linear in this variable A alpha beta. So A alpha beta is just some variable, A1, 2, maybe. Then we define merge alpha beta of F1, F2 as f1 g2 minus f2 g1. So this combination, it's set up to kill this term. So to kill the term that contains a alpha beta. So the variable a alpha beta will disappear from the merge thing. And then also it's like clearly if f1 and f2 are in some ideal, then the merge is also in the ideal. So so let me define the spread of some polynomial f in this polynomial ring, a11 through ann, is just the variables appearing in f. And then so it's, maybe I'll denote it's a spread of f. So it's just, you write out your polynomial in terms of like the monomial basis, and then you ask which variables appear. And then the property of this merge is that the spread of the merge of f1 and f2, it's contained in the union of the spreads. So you don't introduce any variables that didn't appear in either f1 or 2, but the variable alpha beta no longer appears in the merge, and so you've eliminated that. So okay, so now I can state what we show, the set that we consider. So what you do is you start out with the CDD generators, and then you merge them in any way such that you have two CDD generators, and they determine some sets of rows and some sets of columns. And if the spreads of the CDD generators that you start with only intersect in like basically one square, so there's like a unique row and column and a unique column in common, then you can merge them and you get a new polynomial, and you add that to our set of polynomials. Okay, so let me do an example. So suppose I is equal to 426153. So I will draw the Roth diagram. So 4, 2, 6, 1, 5, 3. So the like 0, 0, 0. And then this is a 1, and this is 2. This is 2. So I can take the CDG generator corresponding to this 3x3 minor. So that means so what that means is you take this 3x3 matrix, you set this this coordinate equal to 0, and then you take the determinant. Okay, so that is an element of the ideal of XW. And then I can take the CDG generator corresponding to this 3x3 minor. So these 3 rows. So again, you set take the determinant of this 3x3 matrix, except you first set this variable to 0. And then you can merge them. So the spreads of these two guys intersects in exactly one square, exactly this square, and then they share exactly this row in common and exactly this column in common. There are no other like rows or columns in common. And then when you merge them, what you get is this polynomial. Okay. And so then you do that. So this is some polynomial in the ideal of this matrix Schubert variety, and so you sort of repeatedly do that. It turns out that in this case there are exactly 2 polynomials, which this set RW, so this collection of polynomials that we're defining, it contains this guy, and then also the guy where you sort of swap these two. So you have A 2, 3, and A3, 2. And then also the CD degenerators, and that's it. So, and then our theorem is that if pi is a permutation where the Schubert polynomial of pi and the Schubert polynomial of pi inverse have all coefficients equal to 0 or 1. 0 or 1, then the set R pi is a universal Groebner basis. Okay, for xw, for x pi. Okay. Okay, so maybe I should say that this the strength of this theorem depends a lot on how interesting or how complicated the class of permutations satisfying this condition is, where both the Schubert polynomials of pi and pi inverse is 0, 1. So we have a there's a description of this class in terms of pattern avoidance, which is essentially due to Avery Saint-Dizier, Carola Meseros, and Alex Fink. So it's given by avoiding like a bunch of patterns. We also have a positive description of what these classes look like. So this is like a picture of a large permutation in this class. So this pi, so for this permutation pi, sigma pi and sigma pi inverse are 0, 1. So I'll go for 0, 1 for this pi. So basically what it the sort of main, the most basic examples of permutations pi which satisfy this are the permutations which give either the locus of rank 1 matrices or the locus of co-rank 1 matrices. So our theorem applies to the locus of rank 1 matrices and the locus of co-rank 1 matrices, and it recovers classically known universal Groebner bases there. So for a general permutation that our theorem applies to, it's like kind of significantly more complicated than either the locus of rank 1 matrices or co-rank 1 matrices. But basically it looks like somehow what you do is you have like some co-rank 1 regions and you have some like rank 1 regions, and then somehow you chain them together in some way. And so there's some sort of explicit description of what it looks like, and it's not, most permutations do not satisfy this, but it's not like it's not so restrictive as to be like a trivial class or reducing to some well-known class. Okay, so are there any questions about the statement of the theorem?
So your definition of merge, I was confused about it. It looks like I think it's called an S polynomial in the algorithm used to compute Groebner basis. But then I couldn't quite keep track. It looked like you just got rid of the R's, R1 and R2. So it was not clear if you take two equations of something, then when you merge them, you still have an equation. Or is that just the wrong way of thinking about it?
So I didn't get rid of the R1s and R2s because like F1 is in my ideal and F2 is in my ideal. So both of these polynomials are in the ideal.
Uh-huh.
So it is in the ideal. I mean, if in terms of this thing, the merge is equal to let's see. So it's like R1 G2 minus R R2 G1 maybe. I think that's right. So I think people sometimes call this the S Sylvester resolvent or something. I think it might be the same thing as the S polynomial. Maybe S stands for Sylvester.
Okay, okay.
I'm not
So
sure.
maybe I'm just confused about the notation. But okay, okay.
Yeah.
I'll go with that.
Yeah.
Thanks.
So I mean, yeah. Yeah. The point is you have some variable in common and you eliminate it from by taking an appropriate polynomial combination. Um, okay, so let me let me sort of say what this how we prove this. We don't really, I kind of doubt it's possible to prove this just by like thinking about the algebra and sort of using whatever algorithm to compute Bookberger's algorithm to compute Groebner bases. Um, so so let me just say sort of quickly what our technique is. So it's somehow it's topological. So if I just have an integral subvariety of C to the n, then I could consider the closure inside P1 to the n. Okay? And then I can define the fine multi-degree of X is the uh, you know is the unique square-free polynomial um, f x in variables a1 through an, such that fx evaluated at h, the sort of the generators, the obvious generators of the cohomology, cap with the fundamental class um, is equal to the class of the closure of X. And the so the coefficient, if I take some coefficient of the fine Schubert of this thing, so the coefficient of AX, and this is the degree of some coordinate projection. So this is the degree of the projection from X. So X sits inside affine space, C to the n, and then that projects onto C to the S complement. And then the degree of this map is the coefficient of A to the S. So the coefficient of A to the S is greater than 0 if and only if this map is dominant and the size of S complement is equal to the dimension of S. So size of S complement is equal to the dimension of X. And sorry, and the map is dominant. And so that happens. If this map is not dominant, then that means exactly that there's some polynomial which vanishes on the image. And that means exactly that there's a polynomial which only uses the variables in S complement inside the ideal of X. So this happens if and only if there is a polynomial f in the ideal of X non-zero, which with the spread of f contained in S complement. So i.e. it intersects S trivially. So say that some polynomial f in Ix is a circuit polynomial if f not equal to 0 and the spread of f is minimal with respect to containment. Okay. So if you want to know which coordinate projections are dominant, which is the same thing as knowing like what the support of this fine multi-degree is, that's the same thing as asking what are the possible spreads of polynomials in your ideal. So which variables do when given a set S, is there a polynomial in your ideal which uses exactly S. So it's the same understanding the support of the fine multi-degree is the same thing as understanding, what are the circuit polynomials, or what are their spreads, which variables do they use? And so we prove the following criterion for something to be a universal Groebner basis. So what this says is that suppose you have some subset of affine space, it's an integral subvariety, then the coefficients of the fine multi-degree are all equal to either 0 or 1, if and only if there's a square free universal Groebner basis. So we have by square free, I mean a polynomial, none of whose monomials contains any squares. So like, for example, x1, x2 plus x3 is a square free polynomial. And so what we show is that if you can compute the circuit polynomials and check that they're square free, then they are a universal Groebner basis. And so understanding what the circuit polynomials are is essentially the same thing as understanding what is the support of the fine multi-degree. And so what we do to prove the result is we compute the fine multi-degree of the matrix Schubert variety. So fine multi-degree matrix Schubert variety in the case when pi satisfies our condition. That's the fine multi-degree of. So we call this the fine Schubert polynomial. And then we apply the theorem to deduce that the circuit polynomials are universal Groebner basis. And then, so behind this sort of complicated definition of the merge thing, really what we're doing is we're looking for polynomials in the ideal of the matrix Schubert variety that have like minimal support. And so if you look at this example, this polynomial, its spread, it does not contain the spread of any of the CDD generators. So like a CDD generator, it looks like this, sort of 3x3 minor with a byte taken out of it. And none of those are contained inside here. So, in general, it's like not so clear how to find the polynomials in this ideal, which have minimal spread. But then through this merge operation, we're able to produce a bunch of them. And under, when this condition is satisfied, we're able to show that in fact those are all of the circuit polynomials. Okay, so on there.
Thanks very much. Let's thanks the speaker.